Welcome to Module 10, Optical Architecture and Biogenic Life. This is the module where gemology finally admits it has two personalities. On one side, we have pure physics, light behaving inside rigid, mathematically perfect crystal lattices, cubic, uniaxial, biaxial, all that good stuff. On the other side, we have biology, pearls, amber, coral, materials grown by living organisms that completely ignore crystallography and do whatever they want. So in the first half, we'll map how light travels through different crystal systems, why some stones are singly refractive and some split light into two rays. In the second half, we pivot into the organic world, where structure is messy, durability is low, but the stories are amazing. By the end of this module, you'll be able to explain both why a diamond behaves like a tiny optical machine and why amber can smell like pine sap and melt in hot water. Physics meets biology. Welcome to the full spectrum of gemology. Let's start with the roadmap of light behavior in crystals. When light enters a gemstone, one of two big things can happen. It stays as a single ray, traveling at the same speed in all directions. Or it splits into two rays, each vibrating at right angles and traveling at different speeds. We call the first case isotropic, single refraction. The second case, anisotropic, double refraction. In isotropic materials, the internal atomic structure is so symmetrical that light sees the same environment no matter which way it goes. Think of it like running on an endless, perfectly flat soccer field. No matter which direction you sprint, the ground feels the same. In anisotropic materials, the atomic spacing and bonding change with direction. So light experiences different speeds depending on its path. That's like running through a city. Smooth pavement one way, sand another way, uphill cobblestone a third. Your speed changes with direction, and so does the behavior of light. Key insight from this slide: internal crystal structure dictates optical behavior. High symmetry, simple light behavior. Lower symmetry, more complex light paths. That's the foundation for everything that follows. First up, isotropic systems, the cubic sphere. Technical data: crystal system, cubic, isometric. Optical character: singly refractive, SR. Key examples: diamond, garnet, spinel. In these gems, atoms are arranged with equal spacing in all three dimensions. That perfect symmetry means light always encounters the same density and bonding environment, regardless of direction. Result: uniform refractive index in all directions. No splitting of light. If you could shrink yourself down and ride a photon through a diamond, the terrain would look identical no matter which way you went. So the light ray just keeps going as a single polarized beam. No drama. Practically, this means no pleochroism, no color change by direction. Polariscope tests show the stone stays dark during 360-degree rotation, ignoring strain. Great for simple optical behavior, but less exciting in terms of directional phenomena. Cubic gems are the introverts of optical mineralogy. Neat, consistent, and predictable. Next, we level up the complexity with uniaxial systems, the single optic axis. Technical data: crystal systems, hexagonal, trigonal, tetragonal. Optical character, doubly refractive, DR, uniaxial. Key examples: corundum, ruby, sapphire; beryl, emerald, aquamarine; tourmaline. These crystals have medium symmetry. They possess one unique direction in which light behaves as if the crystal were isotropic. This is the optic axis. Here's the rule. Light traveling parallel to the optic axis, single refraction, no splitting. Light traveling in any other direction, double refraction, splitting into two rays that travel at different speeds. You can imagine the crystal like a city with one perfectly straight highway, the optic axis, and lots of side streets with different surfaces. Drive along the highway, smooth, predictable. Leave the highway, suddenly friction changes, speed changes, and with light, that means splitting. Uniaxial gems are where we start seeing pleochroism, two different colors or intensities viewed along different directions. Orientation decisions in cutting, aligning the table relative to the optic axis to control color and brilliance. Ruby, sapphire, emerald, tourmaline, most of the big colored stones live in this uniaxial world. Now we go full chaos with biaxial systems, two optic axes. Technical data: crystal systems, orthorhombic, monoclinic, triclinic. Optical character: doubly refractive, DR, biaxial. Key examples: chrysoberyl, including alexandrite; topaz, tanzanite, peridot. These crystals have the lowest symmetry and the most complex light behavior. They feature two optic axes, two special directions where light behaves singly refractive. Three principal refractive indices: alpha, alpha; beta, beta; gamma, gamma, each corresponding to light vibrating along one of the three crystallographic axes, X, Y, Z. In most directions, light splits into two rays with different velocities and polarization directions. It's like having three different speed limits, depending on which way you go. What does this complexity give us? Trichroism. Three different colors or intensities when viewed along different directions. Famous in gems like tanzanite and andalusite. Highly diagnostic optical behavior, but more challenging cutting decisions because color and brightness can change dramatically with orientation. Biaxial gems are the drama queens of optics, harder to understand but incredibly rewarding when you know how to read their behavior. Time to use this knowledge in a classic gemologist nightmare: the unknown red stone. Scenario: you're looking at a bright red faceted gem. Is it garnet or ruby? They can look similar to the naked eye, but they live in totally different optical worlds. Step 1. Polariscope analysis. Place the stone under the polariscope and rotate it through 360 degrees. If it remains dark throughout, no light, dark blinking, it's singly refractive, SR, isotropic, likely garnet or spinel. If it blinks light and dark as you rotate, it's doubly refractive, DR, anisotropic, likely ruby or another DR red stone. Step 2. Dichroscope. Check for the SR candidate, likely garnet. View through the dichroscope. You'll see one shade of red only, no matter how you rotate. For the DR candidate, likely ruby, view through the dichroscope. You'll see two shades of red, classic pleochroism. So the decision tree is SR in polariscope plus one color in dichroscope, garnet or spinel. DR in polariscope plus two reds in dichroscope, Ruby. No guesswork. No, I feel like this is ruby. Just physics. That's your diagnostic toolkit in action. Now we slam on the brakes, exit the crystal highway, and enter the jungle. Organic gems. These are not formed in the Earth's crust by heat and pressure. They are byproducts of living organisms. Key differences from mineral gems. Structure, often aggregate or amorphous, no long-range crystal order. They do not obey crystal system rules. There's no cubic, trigonal, or hexagonal symmetry to lean on. Durability, generally low hardness and sensitive to environment, heat, chemicals, and rough handling. Composition, built from proteins, calcium carbonate, and fossilized resins, not from silicate or oxide mineral lattices. So while mineral gems are like meticulously engineered skyscrapers, organic gems are like coral reefs, tree sap, and seashells that time and chemistry hardened into jewelry materials. Beautiful? Yes. Predictable? Not so much. From here on, think less optical physics lab and more natural history museum. First organic gem. Pearl. The ocean's version of a security system that accidentally became luxury jewelry. Formation. Pearls are formed by mollusks, oysters, mussels, when an irritant, like a parasite or bit of shell, gets inside their soft tissue. To protect themselves, they coat the irritant with layer after layer of nacre, also called mother of pearl. Structure diagram on the slide. A nucleus, irritant, in the center. Surrounding layers of nacre composed of thin aragonite platelets, CaCO3, held together by conchiolin, an organic glue. Optical magic. The famous nacreous luster and orient, that soft, rolling rainbow sheen, comes from light interfering in those ultra-thin nacre layers. It's not just reflection, it's optical interference, like an oil slick or soap bubble, but engineered by a mollusk. Warning: chemical sensitivity. Pearls are absorbent and made of calcium carbonate. Acids dissolve them. Vinegar, lemon juice, even prolonged contact with skin oils can dull the surface. Cosmetics and perfume. Always apply perfume and hairspray before putting on pearls. Don't marinate your pearls in chemicals and then ask why they look sad. Pearls are basically luxury chalk with an attitude. Treat them gently. Next, amber, the original save file for prehistoric life. Formation. Amber is fossilized tree resin, not sap, from ancient coniferous forests, typically 30 to 90 million years old. Over millions of years, resin undergoes polymerization. Its molecules cross-link and harden, transforming sticky resin into solid amber. Inclusions. Amber is famous as a biological time capsule, trapping insects, plant fragments, and air bubbles as they got stuck in the sticky resin. Every inclusion is a tiny snapshot of life from tens of millions of years ago. Jurassic Park made it famous. Gemology makes it real. Warnings. Heat and solvents. Heat. Amber softens at relatively low temperatures. Never steam clean amber jewelry. Solvents. It is soluble or damaged by alcohol, acetone, and paint thinners. Many commercial jewelry cleaners will destroy its surface. If a client's gemstone comes out of an ultrasonic cleaner sticky and smelling like pine, guess what? You just rediscovered its resin origins. We'll see that in a scenario later. Now we head underwater again, with coral, the skeletal branch. Formation. Coral is built by colonies of tiny marine organisms called polyps. These polyps secrete calcium carbonate to form a hard, branching skeleton that protects them. Essentially, a biogenic rock. Varieties. Precious coral, Corallium rubrum. Dense, durable, with intense red to pink colors. Traditionally used for high-end jewelry. Common coral, very porous and sponge-like. Often needs dyeing or stabilization to be usable in jewelry. Warning: porosity and acid. Coral is highly sensitive to acids, just like pearl and other CaCO3-based materials. Porous corals will absorb liquids, oils, and dirt permanently. You can't clean out what has soaked into the structure. Abrasive wear can easily scratch and dull the surface. Think of coral as beautiful but introverted. You can take it out, but treat it very, very gently. This slide draws a bright line in the sand. Organic gems live in the tender zone of hardness. Organic gems hardness range: amber 2.5, pearl 3, coral 3.5. These values are all well below 5 on the Mohs scale, meaning they scratch very easily. They are not suitable for rough wear, everyday rings, or abrasive environments. Key message: organic gems require special care. No rough cleaning, no harsh cloths, no aggressive jewelry boxes. Avoid abrasion, hard knocks, and "I just toss all my jewelry into one pouch" habits. If mineral gems are your everyday sneakers, organics are silk slippers, beautiful, but strictly indoor shoes. Contrast that with mineral gems, which dominate the tough zone. The slide's Mohs scale highlights: 7. Quartz and dust. Beryl, topaz. Corundum, sapphire, ruby. Diamond. Here's the crucial note. Household dust is approximately Mohs 7. Anything softer than 7, including all organic gems, can be scratched just by wiping off dust with a dry cloth. That means cleaning a pearl or amber with a dusty shirt is basically sandpapering your gem. Understanding this scale isn't trivia, it's damage prevention. Diamond, corundum, chrysoberyl, excellent daily wear. Beryl and topaz, good with some care. Everything softer than quartz, especially organics, should be treated like fine art, not hardware. Next master table: organic materials, what they're made of, why they're special, and how not to accidentally destroy them. Pearl composition: CaCO3, aragonite, plus conchiolin. Key feature: nacreous luster and orient from thin layer interference. Critical care: avoid acids and perfumes. Put on cosmetics before pearls. Amber composition: fossilized tree resin. Key feature: inclusions, static electricity. It can attract dust when rubbed. Critical care: avoid heat and solvents. No steam cleaning, no alcohol-based cleaners. Coral composition: CaCO3, calcite, built by polyp colonies. Key feature: skeletal, branching structure. Can be dense, precious, or porous. Critical care: avoid abrasives and acids. Porous varieties stain permanently. If the mineral table was about physics, This one is about biography and first aid. Memorize these 3 lines and you will save many clients from tragic cleaning stories. All right, let's wrap this module with some real-world puzzles and a big picture reminder of what you've actually learned. Scenario A. The red mystery stone. Picture this. A client hands you a bright red stone and says, "Is this a ruby?" You smile, walk over to your polariscope and start the magic. You place the stone in the polariscope and rotate it through 360 degrees. It stays dark the entire time. No blinking, no light-dark changes. What does that tell you? The stone is isotropic, singly refractive, not doubly refractive. That means it's almost certainly not ruby, because ruby, corundum, is doubly refractive. Your prime suspects now become garnet or spinel, both cubic and singly refractive. One simple observation, stayed dark on rotation, just knocked ruby off the table. That's the power of optical architecture. No drama, just physics. Scenario B. The sticky pine-smelling gem. Next scenario. A client proudly tells you they cleaned all their jewelry together in the ultrasonic cleaner. One piece comes out sticky and smells like pine. That smell is not aromatherapy, that's your diagnostic clue. What happened? The stone was amber, fossilized tree resin, not a mineral. The ultrasonic introduced heat and solvent action, which softened and partially dissolved the resin, releasing that pine scent. Result? Surface damage, sticky texture, and a very sad piece of jewelry. Your diagnosis: amber, damaged by heat, solvent in ultrasonic cleaning. Moral: if it behaves like old resin and smells like a forest when heated, treat it like amber and keep it away from aggressive cleaning. Scenario C. The two-tone green gem. Last scenario. You examine a green stone with the dichroscope. Instead of one uniform green, you clearly see 2 different colors in the windows: blue-green and yellow-green. What does that tell you? The stone is doubly refractive and pleochroic, 2 distinct colors. DR behavior. In the world of green gems, that strongly points toward emerald, beryl, or green tourmaline, both anisotropic and pleochroic. So with one quick instrument, you've ruled out isotropic imposters like green glass or certain garnets and narrowed it down to a small, high-value club of DR green stones. Now, zoom out and look at what ties all of this together. On one end of our spectrum, you have the precise atomic alignment of a diamond, cubic symmetry, a single refractive index, and light paths you can model with neat diagrams and equations. On the other, you have the chaotic, time-preserved biology of amber, sticky resin turned fossil, trapping insects and softening in a warm, ultrasonic bath. To be a competent gemologist, you have to be fluent in both worlds. The physics of light in crystals, isotropic versus uniaxial versus biaxial, critical angles, and diagnostic tools like the polariscope and dichroscope. The natural history of organics, how pearls, amber, and coral form, what they're made of, and how easily they can be damaged by dust, acid, or heat. The course has given you 2 key revision tools for this. The Optical Architecture Master Table, crystal system versus optical character versus key gemstones. The Organic Materials Master Table: composition, signature features, and critical care instructions. These aren't just exam cribs. They're your working checklists for the lab and the jewelry bench. So, from a red stone that refuses to blink in the polariscope, to a pine-scented gem fresh from the ultrasonic, to a green stone whispering two colors through the dichroscope, remember, every gem is somewhere on this spectrum between physics and biology. Your job is to read the clues, connect them to structure and origin, and tell the story hidden inside the stone.